Okay, so this will be the first lecture over chapter 14, so ethers, sulfides, and epoxides. So in this lecture, we'll look at just how to name compounds of these functional classes, and we'll look at some of their basic fundamental properties. So first of all, if we look at how to name them, so the nomenclature. So ethers, you basically just name as alkyl-alkyl ether, and the same for sulfide, just the two alkyl groups attached to sulfur, and then in the name with sulfide. So if we take some examples, so in this case, so you have two alkyl groups attached to oxygen, so that's what makes it an ether. So you simply name the two alkyl groups separately. So this would be ethyl ether, or since they're both the same alkyl group, then you would just call that diethyl ether. So when somebody says ether, they're probably talking about diethyl ether. And same for the sulfide. So 1, 2, 3, 1, 2, 3. So two propyl groups. So this would be dipropyl sulfide. Okay, so in this case, it's not symmetric. So we have a 3-carbon chain and a 4-carbon chain. So we have a butyl and a propyl. And so you would want to alphabetize. So that would be butyl, propyl, ether. And so this one, you have a cyclohexyl and a methyl. So again, alphabetized. So cyclohexyl, methyl, sulfide. Okay, so a little bit more complex. So 1, 2, 3. So you would name this alkyl group just like you would normally. So you would have a propane as the parent with a bromine on carbon number 2, but then that would become 2-bromopropyl. And then on this side, cyclopentyl, and then ether. Okay, so now we have two functional groups in the molecule. We have an alcohol and an ether. And so now you have to know which one has priority, because one will be part of the parent and the other will be as a substituent. So the alcohol has priority over the ether. So the alcohol is going to have priority. So you're going to number it, that carbon number 1, and then this will be a substituent on the alcohol parent. So when ethers don't have priority, then you call them oxy. So whatever the alkyl group is, in this case it's 3 carbons, propane. No, it's 2 carbons, ethane. Right, 1, 2. So that would become F-oxy. So on carbon number 3, you have an ethoxy group, and then so the parent propane. If you remember how to name alcohols, you change the E ending to OL. So that would be a propanol, and it's at carbon number 1. So you would put a 1 right before the O, because the OL is what tells you it's an alcohol. So that would be propan-1-ol. So 3-ethoxypropan-1-ol would be the name of that molecule. Okay, so this next example is similar. You have an ether and you have an alcohol. The alcohol has priority, so that's carbon 1, 2, 3, 4. So 1 carbon would be methane for the 1 carbon there. And so since it's a substituent, then it would become methoxy. So you have a 4-methoxy cyclohexanol, right? So cyclohexane. The E would become OL. And so in the ring compound like this, it's understood that the OH is at carbon number 1, so you don't have to put the 1 before the OL. Okay, so we're almost done with that name, but not quite, right? There's one thing that we're missing. So what are we missing is stereochemistry. So here the OH is on bottom of the H, and here the ether is on top of the H, so that's opposite, so they're trans. So this would be Trans-4-methoxycyclohexanol would be the name of that molecule. Okay, and the next one, just another level of complexity. So now you have three functional groups. You have the thiol, you have the ether, and you have the alcohol. Which one has priority? Is the alcohol. So if you remember what to call thiol when it doesn't have priority, that's called mercapto. Here you have 1, 2, 3 carbons in the ether, so propane would become propoxy. And now which end do you start numbering the parent from? Is it 1, 2, 3, 4, 5, or is it 1, 2, 3, 4, 5? Well, if you just started numbering from the left, the SH would be at carbon 5, but if you number from the right, it would be at 1. So that would be lower, but that doesn't matter because the OH is the highest priority. And so you always keep the highest priority functional group numbered as low as possible. So you would start numbering at the left so that the alcohol is at 2 and not at 4. Okay, so now let's put this all together. So we have propoxy and mercapto. So mercapto is going to come first in the name. So that's going to be a 5-mercapto. And then a 1 propoxy. And then a 5-carbon chain would be pentane, which would become pentanol. Pentan, and the OH is at carbon number 2, so pentan-2-ol. And then we're still not quite done, right? Because this molecule has a chiral carbon in it, so we need to determine the stereochemistry. So stereochemistry of the chiral carbon. So the OH is priority number 1. And then this is going to be number 2, and this pathway number 3, and hydrogen's number 4. Right, so even though the sulfur has higher mass than the oxygen, it doesn't matter because you go to this carbon and that carbon, and those are the same, so then you go to the next position. Well, this carbon goes to an oxygen, and this carbon goes to another carbon, and so oxygen beats carbon, so the ether pathway has priority over the mercapto pathway. So 1 to 2 to 3 is clockwise, that would be R. 4 is in the back, so the arrow stays clockwise, so this would be R. 5-mercapto, 1-propoxy, pentan-1-ol would be the name of that molecule. Okay, cyclic ethers. So this one is the first one you should recognize, that is an epoxide. Epoxides are also called oxiranes, so that's also an oxirane. If it's a 4-carbon ether, that's called an oxetane. A 5-carbon ether, that's called an oxalane. This particular one is called THF. That's an acronym for tetrahydrofuran. If you remember, we've talked about this before. That's a common solvent in organic chemistry. And the 6-membered ring ether is what's called an oxane. This one's called tetrahydropyran. And then you see this ether sometimes, well, this is a common solvent in organic chemistry as well. That's called dioxane, or more specifically 1,4-dioxane. So the sulfur versions, so basically just take the ox at the start and change it to thi. So if we change the ox to thi, then this would be a thiarane. And same here, change the ox to thi. So 4-membered ring with sulfur is a thiatane, 5-membered ring is a thiolane, and 6-membered ring is a thiane. But I'm not going to expect you to know those. You should basically know the epoxides, because we're going to talk a lot about epoxides, and we're going to look at how to name epoxides in just a minute. And you should know THF because it's a very common solvent in organic chemistry, and you should know dioxane because, again, it's a common solvent in organic chemistry. But I won't expect you, I'm not going to ask you to know the names of the other ones. Okay, so let's look at how to name epoxides. So there's 3 basic ways to name epoxides. You can name them as an oxirane, or you can name them as an epoxide, or you can name them epoxy. So we'll look at a way to name this molecule using all 3 methods. So if you wanted to call it an oxirane, so oxygen's number 1, and that's 2, and that's 3. So you would have a 2-methyl, and then just stick oxirane at the end. Or naming it as an epoxide is similar. You would just call this 2-methyl epoxide. And if you wanted to use the epoxy method, that's a totally different way to name. So what you do, if you're naming it as an oxirane or epoxide, then that is the parent, right? If you're using the epoxy way to name things, then that is the parent. The carbon chain is the parent, and the epoxy is the substituent on the parent. So in this case, that would be carbon 1, 2, and 3, so that would be a propane. So you could name this as 1, 2, epoxy propane. Right, so the epoxide oxygen bridges carbon 1 and 2, so that would be 1, 2, epoxy propane. So if we did the same thing for this one, if we name this epoxide using all 3 methods, then we could say, so we have a methyl and we have a propyl. So that's carbon 1, so what's going to be carbon 2? So it's going to be 2, 3 either way you go. So we want to resort to the alphabet then, since this is going to come first in the alphabet and then that. So then it's going to be a 2-methyl 3-propyl oxirane. Or you could call it 2-methyl 3-propyl epoxide. Or the other method to name it would be to consider this the parent. So you'd have 1, 2, 3, 4, 5, 6 carbon chain parent with a epoxide between 2 and 3, so you could call that 2, 3 epoxy hexane would be another way to name that. Okay, and for this last epoxide, so again, we could treat this as the parent. Sorry, let's make this hydrogens here. So then you would have either cis, that would be carbon 1, 2, 3, so 2, 3 diethyl epoxide, or you could say cis 2, 3 diethyl oxirane. Or this does have 2 chiral carbons, right? And it's got an internal plane of symmetry, so you could say meso here as well. Okay, so meso, and then all of that would be the same. And that would be the even better way to name it. But cis is sufficient here as well, because if the 2 alpha groups are on bottom, that's the same molecule and it's still cis to each other. Okay, and then the other method would be to consider the carbon chain the parent. So if that's the parent, then 1, 2, 3, 4, 5, 6, so 6 carbon chain again. So meso, and then the epoxy is between carbon 3 and 4, so 3, 4 epoxy hexane would be the name of that molecule. So again, you should know all 3 ways to name epoxides, using oxirane, epoxide, or using epoxy. Okay, so if we look at the basic properties, so some of the fundamental properties of ethers. So if we compare these 2 ethers, right, so when we look at basic properties, we're going to be looking at things like boiling point, H2O solubility. So in terms of boiling point, well, the one with the more surface area in this case, since they had the same polar group, then you can resort to surface area. So the one with the more surface area, you can see has the higher boiling point. So diethyl ether is a boiling point of 34.6, whereas dimethyl ether is a gas at room temperature, boiling point of negative 24 degrees Celsius. So the basic structure of ethers, so I drew them linear here, but of course they're not linear, right? That oxygen has 4 things attached, so the 4 things would be arranged tetrahedrally, 2 lone pairs and 2 atoms attached to oxygen, but the structure would be bent, right? So it does have a dipole, right? Because oxygen is more electronegative than carbon. So it's pulling electron density off of carbon like that, and electron density off of carbon like that, and the net dipole would be in that direction. So they have some polarity to them, but they're not very polar molecules. So in terms of water solubility, so if we compare the dimethyl ether than the diethyl ether, the one that's more water soluble would be the dimethyl ether, because it's got less hydrophobic surface area, right? It's only got 2 carbons versus 4 carbons, so it's going to be a little bit more water soluble. But the diethyl ether does have some water solubility to it. So 6 grams of this will dissolve in 100 grams of water. And we've talked about this before. Why does it have any water solubility at all? Because it can make hydrogen bonds to water molecules, right? So hot water can provide the partial positive hydrogen, and oxygen of the ether, the partial negative atom with lone pair. So it can make hydrogen bonds to water, so that's going to give it some water solubility. But it's not highly water soluble. So after 6 grams, then anything after that is going to form a separate layer, and you would have 2 layers. All right, so if you had some diethyl ether and water, and so diethyl ether is used as a solvent all the time in organic chemistry, so you can use it for extractions. So if you had a diethyl ether water mixture, so if we had 100 grams of diethyl ether and 100 grams of water, so there would be 1.5 grams of water dissolved in the ether, so it would actually need then 101.5 grams of water, right? So 100 grams would remain as a separate phase, and 1.5 grams of water would dissolve in the ether. And then 6.05 grams of ether would dissolve in the water layer. So if we had 106.5 grams of ether, 6.05 grams would dissolve into the water layer, and the other 100 grams would form a separate layer on top of the water because it's less dense than water. So if you want a dry ether, where would you want dry ether at? So we've talked about how ethers are used as solvents in Grignard reactions. So that was back in chapter 10, so of Organic 1. So if you wanted to make a Grignard reagent, typically the solvent is ether, and the ether has to be dry. So ether would commonly have some water in it. Where's the water going to come from? Well, if it was ever in contact with water, it's going to absorb some water into the ether layer, or just simply the humidity in the air. If you open a bottle of ether up and it's humid outside, then some water is going to get into the ether. So that's just a practical thing that you have to deal with. If you want to work in lab with ethers and you need dry ether, then you would have to find a way to dry the ether. Okay, crown ethers. So these type of ethers are what are known as crown ethers. Why crown ethers? Because they look like a crown. And if we were to name these, this is called 12 crown 4. This is called 15 crown of 5, and this is did I do that right? Yeah. And 18 crown 6. So where do these numbers come from? Well, obviously the 4 comes from the fact that there's 4 oxygens in the ring versus 5 oxygens here and 6 oxygens here. And then what does the 12, 15, and 18 come from? Well, that's the total number That's the total number of atoms in the ring. So 12 atoms in this ring, 4 of them are oxygen, 15 atoms in this ring, 5 are oxygen, 18 atoms in this ring, 6 are oxygen. So the significance of these, they have lots of practical applications. So because this is in a ring, you have a lot of electron density in the ring, and so these can be used to bind cations. For example, 18 crown 6 will bind potassium ions in them. And so because all the oxygens are partial negative with lone pair of electrons, then they can be used to coordinate to cations. And so the smaller the ring becomes, the smaller the ion is that will fit inside it. So this has lots of practical applications. So we'll just look at two applications. So they can be used as phase transfer catalyst. So if you try to do this reaction, if you took this so that's one octobromide, and try to do an SN2 reaction with potassium fluoride, and use solvent as the benzene as a solvent, then what you get is no reaction. This reaction doesn't work. But if you take a little bit of 18 crown 6 and put it into the reaction flask, then you get a 92% yield. So what's going on? So in order for this reaction to work, so you have F minus basically comes in and attacks here and kicks bromine out. So the issue here is if you have benzene, well, potassium fluoride is an ionic compound. It's very polar. Will it dissolve in benzene? And the answer is no. So you would have insoluble potassium fluoride. The 1-bromo octane is very nonpolar, so it will dissolve in benzene, but the potassium fluoride will not, so they can't react with each other. So what happens if you put some 18 crown 6 into the flask? So if you add some 18 crown 6, then what happens is the potassium can be bound by the crown ether, and then if potassium goes into solution, then fluoride has to go into solution as well. So you have now what's called a naked anion, because the potassium is solvated in the sense that it's bound by the crown ether. So basically this is serving as a phase transfer catalyst. So the crown ether is picking up potassium from the solid phase, and then the fluoride has to go into solution with it because you have to maintain charge neutrality. And so now you have an F minus in solution, but it's not bound by anything, so now it's free to react with the 1-octobromide and displace the bromine, and you make the product. And then you get a potassium bromide. So the potassium bromide will start precipitating out of solution, and the potassium fluoride will start going into solution, so that the reaction is facilitated that way. So in this sense, the 18 crown 6 it's not being used up. You still have the 18 crown 6, but it is facilitating the reaction, making it faster, so it's a catalyst. And what does the phase transfer mean? Well, it's transferring things from the solid phase to solution. So now it's in solution, and it's catalyzing the reaction in that way. You also find these used for environmental remediation. So there's a lot of sites, for example, that are contaminated with toxic metals. So if this represents a lake contaminated with a toxic metal, and so there's many toxic metals present in the environment. You have lead, mercury, cadmium, chromium, radioactive metals, and so there's many sites throughout the United States, throughout the world, that are contaminated with toxic metals. And if you want to be able to use that lake for drinking purposes, or if you want to eat the fish out of the lake, for example, then you have to get rid of the toxic metals first. So how do you get rid of the toxic metals? Well, one thing that could be done is you could take crown ethers and you can embed them in membranes, and then you can take the lake water and pump it through these membranes. And so what's going to happen is the crown ethers is going to bind these metals, and so then the water that comes out is now clean, and you can pump it back into the lake. So basically you would just build like a mini factory beside the lake, and you could pump the toxic lake water through these membranes that contain the crown ethers, and they can extract the toxic metals from the water and just keep those running until the toxicity level drops to a sufficient level where it's no longer toxic to human or aquatic life anymore, and then the lake becomes usable again. So there's lots of applications in environmental chemistry of this type of of chemistry, using them to clean the environment up. And that's one area of my research interest. One of my research interests is finding ways to detect toxic anions in the environment, and then find ways to extract them from the environment. Okay, we'll stop there.